In this video, we will discuss about reinforcement learning in machine learning. We will cover introduction of reinforcement learning, learning models, motivation, reinforcement learning framework, Q, learning algorithm applications, summary. Models of optimal behavior. 3. Average reward model. Reward per action is considered infinite. Future is taken into account. Rewards in the future are equally valuable. The learning task in reinforcement learning. In reinforcement learning, the learning task involves executing actions, observing outcomes, and learning a policy, pi. Pi that maps states S to actions. A. Aiming to maximize cumulative rewards. This process continues indefinitely and utilizes a discounted model for long-term planning. Key elements: execution and observation. Agents interact with an environment by taking actions and observing resulting states and rewards. Policy learning. The goal is to learn a policy, pi. Pi that maximizes expected cumulative rewards for all states. S. Infinite horizon. The learning process continues indefinitely, focusing on long-term optimization. Discounted model. Future rewards are discounted to prioritize immediate rewards, crucial for long-term planning. Approach: action execution. Agents choose actions based on their current policy, pi. Pi outcome observation. Observations of resulting states and rewards guide policy updates. Policy maximization. Through iterative learning, the agent adjusts pi. Pi to improve performance over time. Discounting. Rewards are discounted to emphasize immediate rewards over distant ones, balancing short-term gains with long-term planning. Application. This approach is essential for tasks requiring strategic decision-making over extended periods, such as robotics, game playing, and financial trading. By iteratively refining policies through action execution cycles, agents can effectively navigate complex environments and optimize outcomes over infinite horizons. The value function in reinforcement learning evaluates the expected cumulative reward an agent can achieve starting from a particular state under a given policy, pi. Pi. It helps in formulating the learning task to find the optimal policy, pi. Asterisk operator. Pi asterisk operator. Value function definition, for a policy, pi. Pi, the value function. Pi. V pi. S, represents the expected cumulative reward starting from state. S. Pi. Equals. Pi. Sigma. Equals. 0, infinity. Gamma. 0, equals. V pi. S equals E pi. Sigma t equals 0. Infinity. Gamma t RT. Divides S0. Equals S. Where gamma. Gamma is the discount factor. RT is the reward at time step. T, and pi. E pi. Denotes the expectation under policy, pi. Pi learning the optimal policy, pi. Asterisk operator. Pi asterisk operator. The goal of reinforcement learning is to find the optimal policy, pi. Asterisk operator. Pi asterisk operator. That maximizes the value function. Pi. Asterisk operator. V pi asterisk operator. S, for all states. S. This can be formulated as, pi. Asterisk operator. Equals. Arg. Max. Pi. Pi. For all. Is an element of. Pi asterisk operator. Equals argmax, pi. V pi. S, for all S is an element of S. Reformulation of the learning task, value iteration. Iteratively update the value function estimates based on observed rewards and transitions. Policy improvement. Adjust the policy, pi. Pi based on the updated value function to maximize rewards. Convergence. Repeat until the policy converges to pi. Asterisk operator. Pi asterisk operator. The policy that maximizes. Pi. V pi. Applications. Value functions are fundamental in reinforcement learning algorithms like Q-learning and policy iteration. They guide agents in learning optimal strategies for tasks requiring long-term planning and decision-making under uncertainty, such as robotics, game playing, and autonomous navigation. Q-learning is a model-free reinforcement learning algorithm used to learn the optimal action selection policy for an agent in an environment. It focuses on learning the Q function. QSA, which estimates the expected cumulative reward when taking action in state S. Key concepts. Q function definition. The Q function is defined as equals plus gamma max. Q S A equals R S A plus max a Q S A, where R S A is the immediate reward for taking action in state S. Gamma 0 less than or equal to gamma 1 is the discount factor. S is the next state after taking action A, and max a Q S A represents the maximum Q value for the next state S. Learning process. Initialization. Initialize the Q table with zeros or small random values. Exploration versus exploitation. Balance exploration, trying new actions, and exploitation, using learned Q values to select actions. Update rule. Update the Q value for each state action pair, S, A, based on observed rewards and transitions, plus alpha, plus gamma max, minus Q, S, A, Q, S, A, plus alpha, R plus max a Q, S, A, minus Q, S, A. Where alpha is the learning rate, 0 less than or equal to alpha less than or equal to 1, R is the immediate reward, and S is the new state observed after taking action A. Q-learning illustration. Consider a grid world example where the agent moves towards a goal state G. Actions have a reward of 0 unless moving into the goal state, which gives a reward of 100. Q-table updates. The Q-table is iteratively updated as the agent interacts with the environment, aiming to converge to the optimal Q values that lead to the goal state with maximum cumulative reward. Example values. Value of Q and V with gamma equals 0.9. Gamma equals 0.9, given the grid example. 0-100G 000. 000. The Q values and V values would be computed based on these rewards and the Q-learning algorithm, aiming to maximize rewards while navigating from the starting state to the goal state. Learning step. Since an absorbing state exists, learning will consist of a series of episodes with a random start state. Uncertain state transitions. State transition probability function is used, denotes the transition probability from state S to S when action A is performed. Q function is modified to application cell phone channel allocation, COBIT, a social reinforcement learning agent, car simulation, using reinforcement learning, network packet routing, elevator scheduling, use of RL to improve the performance of natural language question answering systems, reinforcement learning methods for military applications. Cell phone channel allocation learns channel allocations for cell phones. Channels are limited allocations affect adjacent cells, want to minimize dropped and blocked calls. Cell phone channel allocation, next part. States occupied and unoccupied channels for each cell availability, number of free channels for cell actions, call arrival, evaluate possible free channels, assign one that has highest value, call termination, free channel, consider reassigning each ongoing call to just released channel, perform reassignment, if any, with highest value rewards and values reward is number of ongoing calls. Performance comparison, FA, BDCL, and RL. Fixed assignment, FA method, assigns resources statically without adapting to changing conditions. Advantages, simple implementation, deterministic behavior. Limitations, lack of flexibility in dynamic environments, suboptimal resource utilization over time. Borrowing with directional channel locking, BDCL method, allows resources to be borrowed based on directional locking to prevent conflicts. Advantages, improves resource utilization by allowing dynamic borrowing, mitigates resource contention. Limitations, complexity in implementation and overhead due to locking mechanisms, may not scale well with large systems. Reinforcement learning, RL method, learns optimal resource allocation policies through trial and error interactions with the environment. Advantages, adapts to changing conditions, learns optimal policies over time, potentially achieves higher resource efficiency. Limitations: requires significant computational resources and time for training. Initial policy exploration may be suboptimal. Considerations: environment dynamics. RL adapts well to dynamic environments compared to FA and BDCL. Resource utilization. BDCL improves utilization through dynamic borrowing, while RL aims to optimize utilization through learning. Implementation complexity. FA is straightforward, while BDCL and RL involve more complex setups requiring careful tuning and training. Application: FA, suitable for stable environments where resource demands are predictable. BDCL, ideal for environments with moderate dynamics and occasional resource contention. RL, best suited for complex and dynamic environments where optimal resource allocation can significantly impact performance. COBIT, a social reinforcement learning agent. COBIT represents an innovative approach to reinforcement learning by integrating social interaction into its learning framework. Unlike traditional agents, COBIT interacts with humans and other agents in its environment, learning from social cues and feedback to improve its decision-making process. Key features: social interaction. COBIT engages with humans and other agents, learning from interactions and feedback in real time. Reinforcement learning utilizes reinforcement learning algorithms to learn optimal policies based on rewards and penalties received from its environment. Adaptability adjusts its behavior and decision-making strategies based on social feedback, aiming to optimize outcomes and enhance collaboration. Learning from humans observes and learns from human behavior, incorporating social norms and preferences into its decision-making processes. Applications: collaborative environments, enhances teamwork and collaboration by adapting to human behavior and preferences. Customer service, improves customer interaction and satisfaction by learning from customer feedback and preferences. Education, assists in personalized learning environments by adapting to individual student needs and learning styles. Benefits: efficiency, optimizes task execution and resource allocation through continuous learning and adaptation. Flexibility, adapts to changing environments and social dynamics, enhancing versatility in various applications. Human-centric design, fosters a harmonious interaction between humans and machines, promoting trust and cooperation. Challenges: ethical considerations, ensuring fairness and transparency in decision-making processes. Privacy concerns, safeguarding personal data and maintaining confidentiality in social interactions. Future directions: COBIT represents a promising advancement in artificial intelligence, combining the power of reinforcement learning with social intelligence to create adaptive and empathetic agents. As technology evolves, further research and development will refine COBIT's capabilities, paving the way for more sophisticated and socially aware AI systems. The basic reinforcement learning model consists of a set of environment states S, a set of actions A, and a set of scalar rewards. Learner take actions in an environment so as to maximize its long-term reward. Any problem domain that can be cast as a Markov decision process can potentially benefit from this technique. Unlike supervised learning, reinforcement learning systems do not require explicit input-output pairs for training.